This is another limit law. We have the limit of a variable or a linear variable is equal to the constant, or the in this case the cluster point, or the value where our x is approaching to. We have been using this also in solving limits in calculus, but this time we're going to prove this using the definition. Now, I'm not going to write here the entire definition, but just a snippet of a definition. It states that for every epsilon greater than 0, there exists delta greater than 0, such that if x is an element of A and the distance between x and c is greater than 0 but less than that said delta, then the distance between f of x and L, where L is the limit and f of x is the function, is less than epsilon. So the goal here is to arrive into this, but of course the first part is to make sure that there exists delta. That is why part of our process later on is a scratch work in trying to determine the correct delta to be substituted, because we need to have that in order for us to arrive to this. In the previous example, for the limit of a constant, we have no restrictions to delta. We just used one. Here, let's find out what would be that delta. Okay, we just need to start with this. The limit of x as x approaches to c is equal to c. Take note, this would be our f of x, and this is your L. That's what we're trying to prove. Hence, for this scratch work here, make sure that we arrive into this so we can have a representation is less than epsilon here. So by substitution, your f of x is x, and you have your minus c is less than epsilon. Okay, so with this, we don't need any other what they call this manipulations. We just need to make sure that our delta later on is represented by a certain form, that if this would be applied here, take note you have x minus c, and x minus c is appearing here. So we just need to put some logic as to what would be the correct form. If there are other manipulations in the next few examples, we need to manipulate it and come up with a representation that would fit our delta here. So let's start. Here, the first part of our proof is again assuming this. Let epsilon be greater than 0. And then we assume our delta. When we assume our delta, it should fit this criteria and this here as well. Now, what would be the correct assumption for our delta? Now, if you're going to look into these two, we have the same expression here, the distance with x minus c, and they are both less than epsilon and delta. Now, if we're going to assume epsilon be equal, delta will be equal to epsilon, that would mean we can simply substitute epsilon here. So in case, this is what would happen next. Then, if x minus c is less than 0 but greater than epsilon, as we substitute it here, we can now continue. Then this part here hopefully will be addressed similar to this item here. So we have then f of x minus L, your f of x is x, minus c must be less than what do you call this one, epsilon. Okay, this is now true because we assume that delta is equal to epsilon. Supposedly this is delta, so delta is greater than that, so epsilon is also greater than this because of this assumption. Take note, in the previous video we assumed delta be equal to 1. Here we assumed delta be equal to epsilon. It's not all the time epsilon. We just need to manipulate this if there are more needed computations. But since we arrived to this, or if you would like to, you could have here delta which is equal to epsilon. Okay, you could have something like that. So, or also you can erase this one here if you would like to. Okay, because this is the statement here. So once you put less than epsilon, delta equal to epsilon, then thus, or you can have here hence if you would like to. Hence, we could have here f of x minus L is less than epsilon, which is actually the target here of our specification. So after this, we just need to finalize with our what do you call this one, our decision, since epsilon greater than 0 is arbitrary, then we conclude that that what we're trying to prove here is this, so that the limit of x as x approaches to c is equal to c. This is the end of the proof using this process. Again, we have the scratch work here, and we may be challenged by the next few items, so just review this in the previous video for your own consumption. Thank you very much for watching.